So let's recall what Pia told us. She told us that 1 teaspoon of baking soda corresponds to about 0.06 moles of carbon dioxide gas. And if you multiply it out, you will discover that corresponds to about 2.6 grams of carbon dioxide. So in the batter that Joanne made, there were about 2.6 grams of carbon dioxide gas. And the question that we have to ask is, where does it go? So from what I can tell, there are basically 3 possibilities. First of all, the gas could dissolve in the liquid. The batter is, after all, composed of liquid, and in principle, the carbon dioxide could dissolve there. Secondly, the gas could go into bubbles. It could cause the bubbles to puff up. It must get in the bubbles eventually because we know that's what happened in the cake, but that doesn't mean that it goes in initially. We have to think about that. The third possibility is that, of course, the gas could escape. It could get out of the cake entirely and not be useful for baking. So let's think about the third one, number 3, first. That's, in a way, the most difficult, but it's also the simplest to dismiss. So it's certainly the case that in cakes, some of the gas is going to escape. We don't really know how much of the gas is going to escape, but some of it simply has to escape during the baking of a cake. You can sort of estimate that based on what Pia told you. I mean, if you had 2 liters of batter and you produce a liter of gas, you can measure the volume of your cake afterwards and see if it's smaller than 3 liters. I'm sure that it is. And that's sort of the amount of gas that you must have lost. On the other hand, it's worth noting at this point that in other baked goods, not as much gas is lost. So for example, you'll also recall Joanne's demonstration for us of bread making. And there she showed us the little bubbles that form on the outside of bread. The gluten is so strong that the bubbles actually just expand under the pressure of the gas. The gas there, of course, comes from yeast. It doesn't come from carbon dioxide. But anyway, it's still gas. And those bubbles are, and their gas is actually being trapped more clearly in order to keep the bread dough rising. So let's now turn to reason number 1, which is dissolution. So how much of the carbon dioxide gas, the 1 liter of carbon dioxide gas that's produced in this recipe, actually dissolves in the batter? So in order to see this, what we need to do is revisit an old friend, a concept that we discussed in week 3 of this course. Hopefully you all remember back that far. There we talked about solubility, and we talked about the fact that molecules could dissolve in a liquid, and the amount that they could dissolve was called its solubility, and we made an analogy to that of an actual gas, you'll recall in week 3. So let me show you here in this plot the solubility of carbon dioxide gas in water as a function of temperature. So because you know, of course, that when you're baking, you're starting out at about, I don't know, 23 degrees or so, and clearly the cake heats up to well above 60 degrees, if not hotter, in the center as it cooks, depending on exactly your recipe and heating protocol. Now, at room temperature, it turns out that about 1.5 grams of carbon dioxide dissolves in a liter of batter. 1.5 grams. Whereas if you go up to much higher temperatures, so another reasonable temperature to look at is 60 degrees, because that's the temperature where eggs start denaturing and these reactions start occurring. And there it's about 0.5 gram of carbon dioxide. So what does this mean for Joanne's recipe? Well, remember, Joanne's recipe had 2 liters of batter in it. And so in 2 liters of batter at room temperature, that means you can dissolve about 3 grams of carbon dioxide gas. Well, that's more gas than actually is produced by the baking soda reaction. So this is sort of remarkable. So it means that initially the baking soda is essentially going to be, the carbon dioxide gas from the baking soda is going to be dissolved in the batter. I mean, we don't know this for sure, I should say. We've never gone and looked. But if you think about it, the reactions must be, I guess, occurring within the batter. And it's certainly reasonable, which are in the liquid, that is to say. And so it's reasonable to imagine that the gas is initially just completely dissolved in the liquid. So this means that initially in the batter, the gas is in the liquid. You're not actually pressurizing the air bubbles, the little bubbles that you've made at all. They're just sort of hanging out for the ride. Now, as you start to heat the cake, though, the situation changes, because then the solubility goes down. And when the solubility goes down, the molecules of gas in the batter have to go out, and they start to fill up the bubble. And when they fill up the bubble, now the pressure in the bubble is larger than it was before. And this, of course, will cause the bubble to expand. So what you must admit about this process that I've just described is that it's really very subtle. Initially, the dissolved CO2 is stuck in solution, and depending on how you heat it, the bubble, it will start to outgas and heat up and expand the bubbles. Now, while the bubbles are expanding, they are out of equilibrium, and so it's now not true, right, that the pressure difference between the inside and outside of the bubble is balanced with the surface tension. If that were true, the bubble wouldn't grow. Instead, these two are unbalanced. The pressure difference, delta P, P out minus P in, is bigger than 2 sigma over R. And so something must balance that mismatch. And indeed, the thing that balances it is our good friend from 2 weeks ago, the viscous stress. Because you see, as the bubble grows, it's actually pushing the batter around it out. And that's producing a viscous stress, which is sort of the drag force that's slowing down the growth of the bubble. And so we can write this down as an equation. We can write down viscous stress, that is from the drag of the growing bubble, is equal to the pressure difference, P out minus P in, minus the surface tension force, which is 2 sigma over R. And this equation, these words can be translated into symbols. It so happens that the viscous stress, if we say that the bubble has radius R, and the velocity of the bubble is expanding at a velocity v, we can write the viscous stress as 4 times the viscosity eta that we talked about last week times v over r. V over r you might recognize as being the shear rate that we talked about when we talked about viscosity. And so this formula, 4 eta times v over r, is really the viscosity times the shear rate, which you'll remember from 2 weeks ago, is the viscous stress. So we can take this equation and we can solve for v, the velocity of the bubble. The velocity of the bubble is delta p, which is the pressure inside the bubble minus the pressure outside, times the radius, minus 2 sigma, the whole thing over 4 times the viscosity eta. And so this formula, what it contains within it is everything that you need to know about how the bubble grows, and we can use it to think about the various scenarios that might occur when you bake. So let's start out with the situation at hand. Namely, we're under the assumption that all of the carbon dioxide gas is initially dissolved in the liquid, then in the batter. When you heat up the batter, then there will be outgassing of the carbon dioxide gas. This occurs, as I said before, because of the solubility curve of carbon dioxide gas. By the time you get up to 60 degrees Celsius, we know that the solubility will be cut by about a factor of 3, and so there will be a lot of gas released, and this will cause the bubble to grow. Now, the gas that's released, though, won't all be released at once, because, of course, it's only coming out as we heat it. So it's going to be gradually released. As you increase the temperature by a little bit, there will be a little more gas released, and a little bit more. There will be a little more gas released, and so on and so forth. And so what this equation will tell us is that the delta P will increase a little, and the bubble will grow, and increase a little more, and the bubble will grow. And that will continue until the end of the recipe. That's the recipe. That appears to be the situation in the recipe that Joanne gave us. So there's one more feature that I want to mention of this equation, and just to really emphasize the complexity of baking. So remember, everything is going to change as we heat the cake. It's not just the outgassing of carbon dioxide. It's also the material constants themselves. Eta, the viscosity, is going to change as we heat the batter. Generally, when you heat things, viscosities decrease, which means it becomes easier to expand as they get heated. However, in a cake, as we've already discussed, the situation is complicated because in addition to making the batter itself less viscous, one is also producing elastic crosslinks between the glutenin molecules and the egg proteins. And this is actually making the batter more elastic. And we haven't talked about that at all. Now, if you think about elasticity, if I have this bubble and the bubble were growing into an elastic medium, the elasticity, of course, will act to squish back on it. It will stop. It will not want the bubble to grow, and it will constrain bubble growth. And so depending on the temperature curve, that is how you're heating the cake, the batter will at some point become elastic and also stop the bubble growths. Hopefully, the summary of this for all of you is that the situation from the point of view of physics is really very complicated. And it's no wonder it takes such talent to cook a good cake. I mean, so the cake bakes, and as the cake bakes, as the batter heats up, we change the solubility of carbon dioxide, which changes the amount of gas that's around. It actually, remember, I haven't even talked about the release of water vapor. That also occurs as you're heating and is well known to be an important part of baking. Water vapor evaporation, of course, occurs with a different rate than the gas solubility constants because water, the phase behavior of water is just different. The viscosity decreases of the batter with a function of temperature. I assert that because that's what generally happens to the viscosity of things when you heat them. Whereas in the case of a cake, the elasticity will increase because all of these elastic networks that we've talked about will start to grow. Getting this right in your cake recipe or your bread recipe is absolutely critical in order to end up with the texture that you need. And at least for me, this situation starts to explain why it is so hard to bake a cake. And I should say, just as a final note, that I focused on the case of only one bubble, but in reality, there are lots of bubbles that are growing all over the place that are each going through a process that like what I've just said. And they, of course, are going to interact with each other and in some complicated way, which sort of goes beyond the simple discussion that I've just given. Some of you might not think it's simple, but it could have been worse.